More in the low power, in the ultra low power, we are talking about nano-watt. Peter is coming from Lakewood University, and we talk about voltage reference with an incredible power consumption.
Okay, hi everyone. So here to present research. So as you see, it's a nano-watt device, and it's a collaboration between three universities: Lakewood University, Universidad de República de Uruguay, and University of Wands in Belgium. So it's basically I had a lot of help. It looks like, hold on a second, you guys skip to the last slide for some reason. Okay, so back to square one. So before I tell you what is a voltage reference, this is the most important consideration in the work. Why are we doing this? Okay. So the why is basically I identify three demands that we have in electronics. We all want stuff that don't take up that much power, don't take up that much space, and still work reliably. So stuff like our cell phones can last longer, our laptops can last longer, temperature sensors can be more reliable, implantable devices can all be smaller. So this is a really big benefit to humanity. Now, one of the fundamental components to make all this possible is a device called a voltage reference. Okay, and what a voltage reference is, just in case you're not sure, it's a device where when you apply a supply voltage to that device, you're going to get an output at some point so that does not change no matter how much your supply temperature, your supply voltage changes. And also, if you took that same voltage and you change the temperature, you will also get that same output regardless of temperature. So this is an ideal voltage reference. Now, how is something like this useful? It's just a device that creates output voltage, right? Well, in applications like analog to digital conversion, the accuracy of this digital output really depends on how constant your reference voltage is. So that's just one example of use for it. And as you saw in another presentation, it's also used for voltage regulators. So that's why we're doing it, and that's what it is in general. Now, how was it designed? Well, common to most designs, we got a current source here going to diode connected load. This current source that we have in this work is a constant inversion level source. So it's basically modern CMOS voltage references are like this. What we used in our design was something called an ACM model. Okay, and this ACM model, it's got a few advantages that we have over regular models for designing circuits like this. It describes the current going into your load as a function of your width-length ratio, something called a ISQ, sheet-specific current. That includes stuff like your outside capacitances, your slope factors, stuff that you really can't control in the design. And there's this special thing here called IF, an inversion coefficient. Now, this IF, depending on the number, it would describe the regions of inversion of the transistor. Like sub-threshold is from 0 to 1, and from 1 to 100 is near threshold, and above threshold is 100. So the advantage of our model that we use for this design is that regardless of your region of operation, you can use the same equations and it will still accurately describe what's going on in the circuit. Okay, so now, how does this work? I need to explain this before I get into the design, really. So now this IF, it's related to the structure of this transistor structure like this. You put in a function, okay, and that function gets related to the terminals of your transistor, right? So this gate is the gate voltage, your threshold, your source, your thermal voltage, and slope factor. Now, if you took this expression and related to your diagram, what you get here is an expression like this, because your source is at ground, so that's 0, and your gate is at your reference, so that's your output. And now, just from this expression, that's where the design of the voltage reference starts. Okay, now this design has two things in it that change with temperature. Like I said before, we wanted the output to not change with temperature. So what we have to do is redefine these terms in terms of how they change with temperature. The threshold voltage itself, that goes down linearly as with temperature. So at 0 Kelvin, there's a theoretical maximum. And then from there, it just goes down more or less linearly as temperature increases. The thermal voltage, as you may know, that's just a linear increase in temperature. So now the question is, you say you took those things and put it back into the original expression. The question is, These temperature-dependent terms, how do we get rid of them? Okay, that's the crux of the voltage reference. We don't want something that changes with temperature. And the answer, the simple answer to that is just make your reference voltage the same as what your threshold voltage would be at 0 Kelvin. And this whole expression boils down to these three conditions here. So now, if these three things are satisfied, theoretically, you're going to get an output that does not change with temperature, and you have a working voltage reference. Okay, but there is a catch. This thing here, this variation of threshold voltage, that does change. Like if you make two microchips, you're going to have different values of this KBT term here. So now, how do we compensate for that? What can we do about the fact that there is change? Well, the answer lies in the fact that this expression relies on the inversion level. Okay, now if you can adjust IF somehow, then no matter what you do, what your process variations, how they are like in terms of affecting the changing your threshold voltage, no matter what, you can somehow compensate for that so that this expression is always true and your output doesn't change with temperature. And then that leads to another question: how do we change IF? Okay, well, you look back into this base expression here. So now, to change IF, there's two ways we can do it. You first of all, you either keep this the same, or change W over L, or keep W over L the same and change I bias. So those are, by those two ways, those two methods, you can change the inversion level of the transistor. Okay, so now let's get all this out of the way. Now, so that's that is the base idea. Now, how is this idea implemented? So we use these trimming transistors here. So now, how it works is, like say, in this topology lets you change the size of the load. So now, if you activated this transistor, okay, then the current will bypass the main part of the load and essentially it gets trimmed, and that's how you modify your W over L. And now the other way, the other method, how do you change the amount of current going to your load? Well, same, in a similar principle where if you apply a signal to this transistor here, then you're going to get more current going into the load. Or if you did not apply the signal, you get less current. So we trim essentially our circuit by these means. Okay, so that's the very general idea of how our circuit works. Now, we didn't stop there. We made the chip. So this is what the chip looks like. And if you zoomed in really, really close to the middle, you're going to get something that looks like this. So there's an NMOS section, a PMOS section, shift registers, and these are in the micrometer scale. And all that required layout work, and we paid close attention to the matching of the circuit. Okay, so you see here, all these transistors, top, down, left, right, they're identical. This is to account for these process variations that could happen when you make a chip. Because it's like 1,000 degrees here, and there's all these random variations. Okay, so the chip was made, and so what comes next is the test. How well does this chip work? Okay, ideally we want something like this. Okay, an output that doesn't change with temperature. And what we got in measurement is this, an output that apparently also doesn't change with temperature. Now, these are the simulated extremes. So now, what that's telling us is in terms of the worst possible process variations, you get these outputs, and these are our measured values. So our measured values are well within our worst case scenario, and this chip works as far as we're concerned. There are two things here. Okay, there's one value that's higher than the other. Why is that? What these represent is when our inversion level has been maximized, and here this one represents when your inversion level has been minimized. And why is one higher than the other is if we go back here, if IF is less, then your VREF is less, and if your IF is more, your VREF is more. Okay, and so in terms of performance, this looks like really close to the ideal, but really, if you look a bit closer, it actually represents 2.79 millivolts of change from 0.9 volts to 3 volts. And also, the current consumption is less than 5 nanoamps, so we do have a working nanowatt device here. Okay, now, what if we took that same output and changed the temperature? So ideally, we want something like this, a straight line. And experimentally, we get something like this. So it looks like 3 lines, but let me explain first. So what we get is that line that increases the temperature is when our inversion level has been maximized, and that line that decreases the temperature is when our inversion level has been minimized. So intuitively, what we know is somewhere between this maximum and minimum, there's got to be a point that changes minimally with temperature. And that point is highlighted here. Okay, so it does look really close to the ideal, but zoom in a little bit, and you'll see that there is some variation. It's about, let's see now, it's 0.54 millivolts of change over 100 degrees. And this performance, this particular performance, is comparable to some of the best works currently out there. And now, in terms of best works, how well does this circuit compare with others? What we have here, this is the performance figures of this work. And in terms of power, performance, and area taken, it's more or less comparable with many of the recent works. Many of the recent works, except for this guy, he's got much less power and much less area than everyone else. However, there's a catch, of course. This process needs transistors of 2 different threshold voltages. Whereas ours, we don't have any special requirements. So basically, the advantage of our design is just another generic way anybody can use these ideas and make a nano-watt power circuit that works very well and does not take up that much area. So all that said and done, what I can say about our work is we made a circuit. It works less than 1 volt, less than 5 nanoamps. So guaranteed, this is a nano-watt chip. And both these architectures, regardless of whether we change the amount of current going to load or change the amount of the width-length ratio, those ideas, essentially what we're doing is changing the inversion level. And we found that both of those methods gave us similar performance. So theoretically, this idea itself is proven to be accurate. One of the things we found out was the change in inversion level that we needed to get to that straight output that doesn't change the temperature. There's actually really big variation. What that implies is if there's a really big variation in IF, there's a really, really big variation in KVT. And that KVT, just in case you forgot, it's just the temperature coefficient of the threshold voltage. And that is news because in our data sheets, they gave us 1 number for this temperature coefficient. It's actually a range of numbers, so this might be useful information for future design. Okay, so before I end, this work was funded by the Natural Sciences and Engineering Research Council of Canada, and it was made by CMC Microsystems. Thanks a lot for your time.
Thank you, teacher. Question?
I have a technical question in regards to the inversion coefficient. You define it as, I think, above 1. You said up to 1, it's weak inversion. I was wondering with regards to the definition, because usually I've seen the inversion factor defined as 2.1 being weak inversion, 0.1 to 1 being moderate, and beyond 1 being strong. I was just wondering if there's a difference in what definition did you use for level inversion. The second question I had was with regards to the subthreshold factor in the equation. Did you assume that that was also changing the level of inversion?
Well, okay, so for your second question first. The subthreshold factor, we assumed it to be a constant value. We do know it changes as your gate voltage changes. However, since the idea of our circuit is no matter what changes are present, we can still adjust it to make it perform well. Even if we assume it's constant and we're wrong a little bit, supposedly we can account for it. We can still compensate for that. Now back to your first question, in regards to the inversion level. I wish I could jump directly to the slide, but okay, here. Let's see now. There, okay. So this is just the ACM model. It's actually a really arbitrary definition. It's like, generally, this 1 to 100 is defined as when your gate is close to your threshold voltage, and 0 to 1 is when your gate is much less than your threshold voltage. Now, I'm not sure which model you're referring to. It might be a different one, but different models, of course, they would have their own definitions of what is weak inversion, what is moderate inversion, or strong inversion. If we're not sure.
The one I was referring to there is reference 2008. It's work on analog, trade-offs in analog design. It defines it in terms of the current transistor over the width of the line. It just defines it as that, and it comes down to 0.1. That's why I was just wondering where this definition came from, because that's one I'm more accustomed to seeing. Again, I was just checking, that's all.
this is, yes, the advanced compact MOSFET model. I think very few people outside of Brazil use this model to design circuits. So what I'm showing here also is this model itself does experimentally prove to be quite valid.
So I was wondering, how do you calibrate that voltage difference? Let's say you're going for like millions of chips. Do you need to calibrate each one, or like?
Okay. Well, in this work, let's see. Let's get to that particular slide. Okay. Now, what we're essentially asking is how were these activated? What we had was basically a shift register that and a data input and a clock. And based on that, we can adjust these one by one. We actually, in this work, did it manually. What I can imagine someone in the future, if they were to do this, is there's got to be some calibration process where these bits can be loaded automatically. I was imagining like a sort of EEPROM that gets saved in it, and as soon as you turn on the device, all the right gates get powered up, and you end up getting the right output.
But you need to test against temperature.
Yes, how we found how we found that one. You see, there's a slope, right? And now in our work, we found the right value based on these slopes. Where the slopes intersect, theoretically, it should be the value of the voltage which doesn't change. And so, I mean, to find this correct value, we had to have changed the temperature a little bit. There may be a more efficient method in where you just do a single test where you go from one test at 80, one test at 0 degrees, one test at 80 degrees. And if you find slopes at these 2 degrees, you can work out what's the correct voltage, and then you find the correct gates to power up.
Because in production, normally we do not test anything in temperatures too costly, because the time constant is too long.
Oh,
What
yes.
you can imagine to make a heater inside, and you have a very fast heating inside your chip, and test your chip against your chip, in fact.
Yes. Well, yeah. I mean, this is like my focus wasn't on what comes next. It was let's make this work. Okay. And future work, that's a good consideration. But if anyone has more questions?
Other question? Thank you, Peter.
Thank you.